Good morning, student. Today our topic is memory management. I am Nilar Mukherjee. Our module objectives will be to understand the overview of memory management, address binding, and contiguous memory allocation and dynamic partitioning, and the compaction, which is a method to deal with external fragmentation, which is a result of contiguous memory allocation. So we have our process, we have our programs. As you know, you have already done the process part, that we have our process are the active entities and the program are the static entities. So suppose this is a program and this is a program that we have installed in our system, so they are in the hard disk. First we need to understand that hard disk, there are several platters, and in each platter, if you see, this is a platter, and in a surface of the platter we have, these are the sectors. This total is a sector, and we have several tracks. These are the tracks. Now in a sector and track cross section we have a block. In that block, data is stored like in a unorganized manner, not unorganized, in a sequential manner, 0 1 0 1 1 0 0 1 1 1 1, like that. So this may be your first instruction, this may be your second instruction, this is your data, but there is no distinguish between them. That's why we cannot run a program from the hard disk itself, run a program or process. So to run a program, suppose you have clicked on the Winamp icon in your desktop. There is a Winamp icon, there is a Chrome icon, you have clicked on your desktop. What happens? Windows have a registry where it has the process program ID and corresponding location where the program is stored. So you have clicked on an icon so the process OS knows that you want to execute that program. First, what it will do? It will create a PCB of for Winamp, but that's a particular instance of that application. So that process will have a PID, and it will give a PID of suppose P1. When you click another instance, another time you click Winamp, that instance will run as another process, will get another PID P2. Both are running for the same program, but said they are different process now. Now for first, OS creates a PCB, and the PCB is now received by whom? The long-term scheduler, who will do what? Who will take the process from the hard disk to memory. Now the point is, as in the hard disk we have the data which is not addressable. In the data we have several instruction and data which are individually not addressable. That's why we cannot run the program from the hard disk. We have to make them addressable. How? So this is our memory. And what are these? For simplicity, I assume that this is, I suppose this is 64 KB memory, and I am talking about a 16-bit system. So 2 to the power 16, that is 2 to the power of 6 plus 2 to the power of 10. So 2 to the power of 10 is 1 KB, and 2 to the power of 6 is 64. That's why we get a 64 KB memory, and this is individual register, and each register of a 16-bit system is also 16-bit. So we can store a 16-bit data here, and we have 0 1 2 3 4 5 6 up to this many of registers in the memory. And using a multiplexer demultiplexer kind of thing, and memory has what? A data bus, which will be also a 16-bit, And so it has a data bus and it has an address bus, which will also be of 16-bit, and data bus will be of 16-bit. I am assuming a 16-bit computer, and there are some control bit, read, write. So when using the 16-bit address line, I can enable a particular register, and depending on whether I'm read is enabled or write is enabled, the data in the data bus, if the write is enabled, data in the data bus will be written in the register. Suppose this register line is enabled, so this register is enabled, and whatever data is there will be written, or whatever data is there will be on the data bus to read for. So when this block gets into memory, so each individual code, instruction or data will be put in a single register, and so they will become addressable. So that's why we need the program to be in the main memory to become ready to run, that is to be selected by the short-term scheduler for execution. So LTS job is to transfer. After the transfer, it will hand over the PCB to whom? To the short-term scheduler, marking that they are now ready to run on CPU. So I hope you are clear up to this. So now the point is how to these are the programs which are now static, inactive, and their PCB is just created. They are handled now by the long-term scheduler, and they are in the state new, and they wants to become ready, and they can become ready when they are transferred to hard disk, and each individual code, instruction or data gets assigned to a particular address. So that we need to understand the address binding. There are three kinds of address binding: compile time address binding, load time address binding, and execution time address binding. Let's see with the graphics. Suppose this is the program that we write, our code 0, code 1, code 2, code 3, like that. This is how we write. Okay? That actually, whenever we are talking about a process or program, don't consider the program you write in your C compiler or Java compiler. Whenever I am talking about a program or process, here that is the linked executable code. That is the when you in the exe file, what you have, that low level machine language code, your one instruction in high level language may be translated into 100 instruction in the low level language. I'm talking about those codes, and those code in your the program, exe program, have their code 0, code 1, code 2, code 3, like up to suppose 100 lines of code. These are the symbolic address of our code. Now there is a relocatable address, that is where my code is in my memory plus my 0th instruction, where my code is in the memory plus my first instruction. So this is the relocatable address. Then finally, when it is actually got into memory, first code gets an actual address, second code get an actual address, like that. So compile time address binding means the compiler does the symbolic to absolute address mapping. Compiler loads. So when the program, if it is moved, we need to recompile. In the load time address binding, the symbolic to reallocatable, that is this from this to this, is done by the compiler, and relocatable to absolute address is done by the loader. So if the process moved during execution, we need to reload. And the execution time address binding that is normally currently used is the symbolic, where the symbolic to relocatable is done by the loader. That is, this part is done by the loader, compiler does nothing, and relocatable to absolute is done by the LTS or midterm scheduler, long-term scheduler or midterm scheduler. That is the OS. Who moves? OS moves a process. Who assigns the physical address? OS assigns the physical address. So when the process moves, actually nothing is to be done. OS will take care of that. How? We will see. Here, when I load process P2 and after some time I load a process P4, then sub P3, then P4. Now somehow P3 is terminated. Then what happens? P4 remains here. Now what to do with this space? This is a hole created inside, and this creation of hole is called external fragmentation. That is creation of hole outside any of the process. This hole does not belong to P2, does not belong to P4. This is outside of any, does not belong to P1. This is a hole outside. That's why external. Fragmentation means creation of holes. So this hole, in this hole, this can be very small or can be large to fit another process. So as we can see, there can be many holes created when the execution goes on. Suppose there were P6 here which terminated, there is another hole here. So there will be several holes created in the contiguous memory allocation. That is we can say contiguous memory allocation or dynamic partitioning suffers from external fragmentation. That is creation of scattered holes in memory. So will we just abandon them? No, we can use them by inserting some other process in them if they fit. Suppose this hole is of 4 KB. Can I fit a process of 5 KB here? No. But there is a process 3.7 KB. Can I fit that in this hole? Yes, I can fit. I may not go here or here. Maybe this is of 6 KB. This is of 17 KB. But I have a hole here which is large enough to fit a 7.3 KB process. So I will put that process here, or I may put that process in the biggest hole, or I may put the process in the hole just enough, or I may put the process just after my last allocation. So there comes a point that where should I put? Where should I put a new process when there are multiple options? That is, multiple holes are there. So we need some algorithm for that. So there are 4 algorithms: the first fit, best fit, next fit, and worst fit. So the problem says we are going to understand this by a problem. So suppose that their memory, there are some processes already there, and what are these? these are holes. And these are external fragmentation, as they are outside of any process memory space. Now the first bit, what it does, it scans. So the according to this problem, suppose this is 287, this whole size is 470, this whole size is 580, this whole size is 650 kb, and this whole size is 740 kb. Now the first fit algorithm for a process, suppose 237 kb, it will start searching from the beginning of the memory, and the first hole where it can fit, it will put the process there. Suppose the process size is 335, it will search here, and it is adequate enough, so it will put the process here. It will search from the beginning till it finds the hole that is large enough to fit that process. In the best fit, it will start searching from the beginning, and it will have to search to the end to find the most appropriate hole to fit the process, that is the hole that is just large enough to fit the process. So it will search starting from the beginning, 287, okay, 470, 580, 650 and 740. When it finds all the hole, then it have to see which of the hole is just large enough. So the smallest hole that is large enough to fit that process is 740, so it will put it there. So there is a time complexity is there, that in every time it has to search the entire memory to find the best hole. This is the worst case complexity. Every time it will have that. The next bit is that suppose I have put the process here, last process I have loaded here, so it will start searching from here, not from the beginning. This is the next fit. So it will search from here and here and here. Whichever hole is large enough to fit, it will fit it there. So as this hole is now large enough to fit 335, it will put it here, not here, because it starts searching not from the beginning, it starts searching from the last allocation, as the last allocation may be P6. Then the worst fit, this just reversed of the best fit, and best fit, there is one uh, disadvantage of best fit or problem of best fit is it tries to allocate the process in a hole which is just large enough to fit. So it will create the smallest leftover holes, which may be so small that no other process can be loaded into or fit into them. So smallest leftover hole is a big problem. So if it loads here, it will create a smallest leftover holes. To fight back with that, there is another case, that is worst fit algorithm. which will again the same as the base fit will start from the beginning to search, and it will search the entire memory, and it will find the largest hole where I can fit. So with what worst fit, it will find that 740 is the largest hole available. So where the best fit will load it here, worst fit will load it here, and this will be the best fit. Also fast fit with fast. So next fit, maybe do it from here. So the best fit, this will be the worst fit, and first fit maybe also here, and next fit maybe here. So this is the 287 kb hole, this is the 470 kb hole, this is the 580 kb, this is 650 kb, and this is 740 kb. So the next bit, if my last allocation is P6, then next bit will find that this is large enough to fit a process 335 kb, so it will fit it here. Worst fit will fit it here, best fit will fit it here, and first fit will also in this scenario will fit the same place, fit in the same place. Let's understand this with this problem. So the problem says the holes are 287 kb, this hole is 470 kb, this hole is 580 kb, this hole is 650 kb, this one is 740 kb. Now the process comes 362, 437, 215, 314 and 576 kb in order. That means at T0 P1 comes, suppose I have P16, P16 comes 362 kb. Using first fit, where to fit that? It starts searching from the beginning and it finds not there. Here it can be fit. Okay, so it will fit it here. So it will fit the 362 kb P1 here. So the leftover will be 470 minus 362, 108 kb. Next process P17 comes, so this is P14. P17 comes, this is 437 kb. So again it starts searching from the beginning. Now this place is occupied. So there is a 287 kb hole, 470 kb, 580, sorry, not 470, 108 kb hole. Now there is a 580 kb hole. It can fit it there, so it will fit it. So it will fit P2 437 kb in this hole. So there will be a leftover of 580 minus 437, 143 kb hole. Then comes P18 with 215. Again it will search from the beginning and it will find it here. It can be fit. It can fit. So P18 215 will be there. So the leftover will be 287 minus 215, 72 kb. Then P19 comes, which is 314 kb, and it will start from the beginning. Start searching from the beginning, and it will find 72 kb hole, which is not large enough. 108 kb hole, not large enough. 143 kb hole, not large enough. Then a 650 kb hole, which is large enough to fit. So it will fit the process here. P19 will be here. So the leftover will be 336 kb hole. Now the last process comes, 576. Again it starts searching. This will not fit, this will not fit, this will not fit, this will not fit. So it will find here it can be loaded. So it loads 576 kb, P20 here. So the leftover will be 740 minus 576, which is 6164 kb. So this is how the fast fit algorithm will work in loading the new processes. Next, so algorithm to study is the best fit. So this is 287, this is 470 kb, this is 580 kb, this is 650 kb, and this is 740 kb. Now the first P1 comes with and again there is a mistake. Suppose this I have considered 14, P14. So P16 comes 362 kb, best fit. So it will start searching from the beginning. It will find this hole is not large enough. Here I can fit it. Okay, go on. Here there is a hole, here there is a hole. In all these 4 holes I can fit the process, but which one is the smallest adequate hole is the 471. So it will put it here, P16 362 kb. So the leftover will be 470 minus 362, 108 kb. Then P17 comes, 437. It will search. Okay, I have a hole of 108, 287. Those are not large enough. 580, 650 and 740, starting from the beginning to end. Then it will find 3 holes and it will have to compare which is the smallest. Now smallest but adequate hole is this one. So it will fit it here. P17 will be there. 437 kb. So 580 minus 437, 143 kb whole. Then the remaining leftover will be 143 kb. Then P18 will come, which is of 215 kb. For that, it will find there is a 287 kb hole where I can fit. Here I cannot fit, here I cannot fit, here I can fit, here I can fit, but the best adequate hole is this one. So 215 P18 K 215 kb will be here, the leftover will be 72 kb. Then P19 will come, which is 314 kb. Now 314 kb, again it will search 72, 108. So P19 will be loaded here. So the leftover will be, there it was 72, here it was 108, it was 143, and the leftover will be 650 minus 314, 336 kb. Then the P20 will come, which will be of size 576 kb. So we will find, best fit will find no holes is adequate enough, only one large hole, so it will fit it here, P20 here, and it will, the leftover will be 740 minus 576, 164 kb. Okay. Next, we are going to consider the worst fit. In the worst fit, when P16 comes, it will find that there is a hole. 362 is the process size, so this cannot be, this hole is not large enough, this hole is large enough, this hole is large enough, this hole is large enough, and this hole is large enough. But the largest hole among them is 740, so it will allocate P16 here. So we'll create the largest leftover holes. So P16 will come here, and so the leftover will be 740 minus 362, 378 kb. Next process is 437. So it will find I have a hole, it will search from the beginning to end, and it will find I have a hole 3878, 650, 580, 740, and this hole is not large enough. Among them, biggest is the 650, so it will load it here. 437, P17 will be here, and the leftover will be 650 minus 437, 213 kb. Then the process come 215. So it will, here it can fit, here it can fit, here it can fit, in this hole it can fit, in this hole it can fit, but among them this is the largest, so it will fit it here. So 215 P18 will be here, and the leftover will be 580 minus 215, 365 kb. And the next process is 314. 314, it will have a 470, 365, 213 and 378. Among them, this one will be the largest, so it will put it here. So the leftover will be 470 minus 740 minus 314, it will be 576 kb. Now the process crumb P is 576 kb. Here you can find that this is smaller, this hole is smaller, this hole is smaller, this hole is smaller, this hole is smaller. So we can never fit 576 in this scenario. So even though we have a big amount of total hole left, 156 kb, 287 kb, 365 kb, 213 and 378. So I have a hole of 287 plus 365 plus 213 plus 378 at around this kb hole I have left with, but still I cannot fit P20. So there is a way that I can fit them? Yes, there is a way. So what problem we are having? We are having scattered holes throughout the memory. The point is, can we collect them together? Now we will see. Yes, so this is the method called compaction. So we have a memory which is already fragmented, having large amount of small holes. So these are the small holes that are being scattered. These are the small holes that are scattered throughout the memory. And they are individually, they are not enough to fit any process. Suppose P15, which is of 5 kb, but their collective size is 17.5 kb, which is large enough to fit not only P15 of 5 kb size, but also a larger process of 11 kb P16, because their combined size is 17 kb, 16 kb. So I can easily fit both of them if we collect the holes. So there is a way. The way is, if there is a way, the way is if we can shift all the process to one end, either to the beginning or to the end, and collect all the holes at the other end, then that method is called compaction. Now the problem is, when we shift, the processes are already loaded here. So P2 will have a PCB, where I will have the PID of P2, and I have the base and the limit. Now I know the OS is of 8 kb, so 8192 is the start of this hole, and the hole is the hole is 3.3 kb. So 3.3 into 1024, it is approximately 3380, which when added to 8192 gives me the start address of this 11572. So the limit, suppose this is 5 KB, so size is 5120 and the start address is 11572. Who does it? LTS when it loads the P2. LTS loads the P2. Now if P2 is moved, shift to this, when it was loaded, when suppose P2 was executing in CPU and generated a logical address 211, how it is moved, mapped to physical address? So we will add 572 with 211 to get 11783, which will be somewhere here. We will access the data. But if it is moved, if I still try to access the data with this address, I will launch in a different data point. So this cannot be done. I need to change the base address. Is it possible? Yes. Because who will shift OS? This PCB is a metadata about the process maintained by OS. So if OS is shifting and OS don't forget to change the base, then it can be shifted. So the way out is, when OS shift this P2, OS will remove this address and it will write 8192 here. So next, when it again try to access 211, it will be, the physical address will be not this plus 8192 plus 211, 3048. So 80403 somewhere here. So it will, so P2 is now here. So it will try to access somewhere here, which will be valid. Similarly, we will have, when we shift P12, it will also have a base and limit. If we don't forget to change its base value, it can be shifted. If when we shift P4, P4 will also have a PCB where it will have a base, where it will have a value. If we erase that and write a new value here, P4 can shift. Similarly, P14, P16, P18, P13. So what we see, if we shift them and don't forget to change the base address, their execution can continue. Their execution will not hamper. That is, the logical address they will generate can be correctly transformed to physical address. So the shifting can be done to either one end, and it is done, and that method is called compaction. So all the process are shifted to one end to collect a large whole of 75 KB, where I now can load P15. Then I can even load P16 of 11 KB. Still I will have 1.5 KB whole left. So using compaction, this will create a overhead, of course, of shifting. What is the overhead? Changing all the base addresses and obviously the more will be shifting all the data. That will take some time, shifting all data one after another. Here data has to be shifted physically and plus changing all the base address value for all process. So this is called compaction. It is used to fight back the problem of scattered. Thank you. Next day we are going to discuss a scheme called fixed partitioning, where we'll have two things: fixed equal partitioning, fixed equal size partitioning, and fixed unequal size partitioning, and which are the building blocks of the larger very good algorithm, that is paging. And we will discuss segmentation, which is an enhancement of this basic contiguous memory allocation scheme to address the scattered holes instead of compaction, which incurs a huge overhead of shifting the data. Is there any way to fight it back with any other way? And that is the segmentation. That is another try to fight it, fight the scattered holes problem. We will discuss in the next module. Thank you.